Hi there, folks. Today we're going to talk about solving inequalities, so multi-step inequalities. But before we start doing that, let's talk about graphing. This should be one of those things that's review, but if it's not, that's okay. We'll run through it, and then we'll practice some of that graphing as we start to solve these things, all right? And really, the graph of these are typically used in the future to be able to kind of check the solutions to some of the more complicated examples that we're going to get, all right? They don't serve a great purpose here, but practicing them now will help us check our solutions when the time comes, all right? So graphing inequalities, we're going to plot the value using either an open dot or a closed dot. We're going to plot it on a number line. And really, the open dot is used when there's no equal to condition. That open dot meaning that point doesn't count as one of our values. The closed dot we use when there is an equal to condition, meaning that point counts as one of our values. All right. So when you think about something be like less than or equal to, that means it could be less than or it could be equal to. So we put a closed dot to signify that that point works. But if it's just less than, we use an open dot because it has to be less than. We can't actually equal that point. So we put an open dot at that point saying, hey, this point doesn't count. All right. And then we shade the appropriate side of the graph. We basically shade the side of the graph where the values we're talking about are. So if it says we want to be less than that value, we have to shade to the left because that's where all the smaller values are. And if it says greater than that value, well, then we want to shade to the right because that's where all the bigger values are. Okay. For example, if I look at something like this guy, I want to go less than or equal to a -4. So again, I'm just going to draw a number line here. And I usually just put -4 right in the center and then do a couple values on each side. Like counting up, that would be -3, -2, -1, 0, 1, 2, okay, that kind of stuff. Going the other way. And that's just a reminder of how negative number works in terms of which ones are bigger and smaller. And now from here, you can do it on the line if you would like. I always do it above the line just so we can see the shading. Technically, it should be on the line when it's all said and done, but doing it above the line will be fine. So less than or equal to, so the equal to condition, that little line underneath there is our equal to condition. Since we have that, we're going to do a closed dot. And then it says x is less than or equal to, so I need to decide where the values that are less than -4 are. Well, less than -4 would be the values that are smaller than -4, so that's this side. So I shade everything on that side. That's the graph of this thing. And basically, the shading is telling me which solutions work. In other words, like if I plugged a -6 in here, I would have -6 is less than or equal to -4, which is true. -6 is less than -4, so it satisfies the condition. And when you say less than or equal to, either one will work. So if I put a -4 in there, well, that would work. -4 is less than or equal to -4. It's equal to -4, one or the other. So if it satisfies either one of those conditions, the statement is true. And that's kind of what the graph is showing us. It's showing us that everything less than -4 works and -4 itself works. That's what the closed dot means. Okay? If I look at the next one, again, we're going to graph this thing on a number line. So I'm going to stick 1 right in the center. And now it says greater than greater than +1. Greater than, there's no equal to condition, so I use an open dot, meaning that point doesn't work, that point doesn't count. But then greater than, I want to find the values that are bigger than 1, which is everything to this side, so I shade it in this direction. And again, if you plug any one of those values in, it works. And notice, it doesn't just cover like 2 and 3, like right here, this point right here, that's like 1.1. If you put 1.1 is greater than 1, that's true. But see, the open dot this time means that 1 doesn't count. Is 1 greater than 1? No, it's equal to, and there was no stipulation said or equal to, which is why we have the open dot. That's why 1 doesn't work, okay? If I look at the next one, again, start with our number line. So I've got -1. Couple values on each side. And now from here, it's less than or equal to. So the equal to condition means I use a solid, a closed point there. And then less than, I'm reading this a little bit backwards. It looks like a less than symbol, but you have to read from the perspective of x. So if you were to read this backwards, it'd be x is greater than or equal to. And one of the things I'll recommend is to always rewrite it. Put the x on the left-hand side, but now make sure of, again, when you first probably saw these in elementary school, we talked about it like an alligator eating the bigger thing. Well, if you look at the original problem, the alligator is eating the x, So if I switch this around, the alligator has to keep eating the x, so it would look like this. Those inequalities are the same thing, and it's really good to practice rewriting those and to remember to keep that symbol facing the direction it was in terms of the value it's facing, not in terms of the way it was facing the original problem. But see, the open end was towards the x. It's got to continue to be towards the x. So this is x is greater than or equal to, so that's shaded to this side. That's where all the bigger values are, okay? Same thing with the next one. I've got my 3. And now from here, again, it's it's written backwards. So again, rewrite it. We'll say x, but then look at which way this thing is facing. I've got the x and the 3 in the original problem. The alligator's eating the 3. So when I flip it around, the alligator has to keep eating the 3 to make this thing the same. Okay? So now this says x is less than 3. So I use an open dot because there's no equal to condition, and then less than means I want to shade to the left. That's where all the smaller values are, okay? So now let's talk about solving these things. Solving these things, if you were good at solving equations, this is absolutely no different. It's the exact same thing. We're going to undo order of operations, work backwards through the order of operations, and undo the operations as we go. The only difference is that if you multiply or divide each side by a negative, we now have to flip the inequality sign. And the reason behind that is because when you change the sign of things, you can do that by actually moving stuff. Like if I have a negative 3, I can get rid of that negative by adding 3 to each side. So I essentially move the 3 to the other side, and it becomes a positive 3. And so what happens with equations, that doesn't matter. But with inequalities, multiplying or dividing by a negative is the same as moving those things from one side to the other. So they switch which side of the inequality they're on, okay? So again, just remember, same as solving equations, but if I multiply or divide by a negative, I have to flip the inequality sign. For example, right here, I've got 1/2 x is less than or equal to 7. Remember a fraction bar is just a division sign. So essentially that's saying x divided by 2. All right, so a 1/2 is the same as dividing by 2. To undo dividing by 2, I have to multiply by 2. Whatever I do to one side, I have to do to the other side. And so over here, it leaves me with an x. Over here, it leaves me with a 14. And now I just copy that inequality sign down the same way that it was. The only time I'll change that is if I multiply or divide by a negative, which I didn't. So it was a less than or equal to condition. I'm going to leave it as a less than or equal to. And now once again, just for a little bit of extra practice, we're going to graph this thing on a number line. And we can start to get a little bit looser with this. I'm just going to put one value on each side now. Getting crazy, right? And so less than or equal to, I close dot because there's an equal to condition. Less than is all the values that are smaller than this, so everything to the left, okay? But this is my actual answer. I just kind of check it on the graph, all right? And again, that doesn't do much here, but it will in the long run, I promise. If I look at this one, right now I'm multiplying by a negative 3. To undo multiplying by negative 3, I have to divide by negative 3. I have to do that inverse operation. So I'm going to divide each side by negative 3. So here I get an x. Over here I get a negative 2. And now normally I just copy down the same inequality sign, but this time I divide it by a negative. So dividing by a negative, I have to flip the inequality sign. So instead of less than or equal to, I'm going to do greater than or equal to. That's it. That's the only difference between this and solving equations. And again, the reason for that is because I could have added this thing to bring it over here and then subtracted this guy to bring it over here. And essentially, it would be me switching sides. Okay, that's why we flip the inequality sign. And you don't necessarily need to know that. You just need to remember to flip it when you multiply or divide by a negative. Okay, and now let's graph this thing. Everybody loves a little bit of graphing. So I've got the negative 2 here, negative 3 would be in this direction, negative 1 would be in this direction. Greater than or equal to, so equal to, I put a closed dot. Greater than is everything bigger than that, so everything to the right. And again, this guy is my answer. The graph is thus there to kind of check it and to visualize what the equation or what the inequality looks like. Okay. If I look at this one again, to undo subtracting 4, I have to add 4. Whatever I do to one side, I have to do the other side. So here I get x is greater than or equal to a 10. And notice the inequality symbol stayed the same that time because I didn't multiply or divide by a negative. And now let's draw a quick sketch of the graph. Why not? After 10 comes 11, and before 10 comes a 9. There's an equal to condition, so I do a closed dot, greater than, so I shade everything to the right. And again, this is my answer. The graph is just a visual representation of that, and we'll use it to check our answers later. Okay, so those are one-step equations. So notice, nothing has changed except for that one in the middle where we had to flip the inequality sign. Same as equations. So when we start introducing more steps, it's still going to be the same thing as equations. With equations, we had to work backwards sort of operations. We had to undo addition and subtraction, then undo multiplication, division, then undo exponents, roots, then undo parentheses or inclusion symbols. And it's no different here. So here, I have to undo the addition first, and I undo adding 11 by subtracting 11 from each side. So I get 3x greater than or equal to. Notice it's still greater than or equal to because I didn't multiply or divide by a negative. And then here that gives me a negative 7. And now to undo multiplying by 3, I divide each side by 3. I didn't multiply or divide by a negative, so I keep the inequality sign the same. And just like equations, you can leave this as an improper fraction here. Negative 7 over 3. Now, when we go to do this on a number line, when we go to graph this, it might be better to think of this in terms of a mixed number, only because that's easier to graph on the number line. So remember, negative 7 over 3 is a negative 2 1/3. And I only do that because, I only think of it that way, because it's probably easier to identify on the number line. I could leave it as a negative 7/3 here, but understanding that that's a negative 2, I could say, oh, that means going this way, that would be like a negative 3, and going this way would be a negative 2. Okay? So kind of getting an idea of where that is on the number line could be important. And then the equal to condition is a closed dot, greater than I shade to this side. But once again, this is my answer. All right? The graph is just there as a visual representation. All right? A little extra practice with it. This one, think of just like equations. I undo subtraction first. So to undo subtracting 6, I'm going to add the 6 to each side. And now to undo multiplying by a negative 2, I have to divide by a negative 2. And here's the only difference between inequalities and equations. I divided by a negative, so I have to flip the inequality sign. Instead of a less than symbol, it's a greater than symbol. And now 16 divided by negative 2 is a negative 8. That's the only difference, is we have to remember to flip the inequality sign when we multiply or divide by a negative. Okay? It's the rule. And now I can graph this thing. Ready? Negative 8 in the middle. Going this way would be negative 9. Going this way would be negative 7. No equal to condition, so I use an open dot. Greater than, I shade to the right. And again, this is my answer. The graph just gives me a visual representation, and I'll use it to check later. If I look at something like this guy, again, think about equations. If this was an equal sign, I would deal with the variables first. I would simplify and then solve. So I simplify by combining like terms. And again, you have to have them on the same side in order to combine like terms. So I can't combine the 6m with anything. But these guys, since they're on the same side, I can combine the 7m and the minus m. So I get this, 6m minus 5 greater than or equal to, looks like a 6m plus 7. So just like we did with equations. And also just like we did with equations, we say, hey, you know what? I'd like to combine those m's, but they're on different sides. To get them on the same side, I have to get rid of one of those m's. So I'm going to get rid of this m by subtracting 6m. That's how we get rid of it. Whatever I do to one side, I have to do the other side. And it just so happens that this time, those cancel and I get the negative 5. Over here, they cancel and I get the 7. Well, we had this same situation happen with equations, and it's the same rule with equations. Remember, with equations, if I got a true statement, it was all real numbers. If I got a false statement, it was no solution. So look at the inequality. It says negative 5 is greater than or equal to a 7. And that's false. Negative 5 is smaller than a 7. It's not greater than or equal to a 7. So this is a false statement, which means the answer here is no solution. If I had a true statement, the answer would be all real numbers. So it's the same thing we've been dealing with equations, just applied to inequalities now, okay? If I look at the next one, again, I can't combine those ends because they're on different sides. So I need to get rid of one of those ends. I'm going to get rid of the 3n. You get rid of the 3n by subtracting 3n from each side. So I'm going to subtract 3n from each side. So here that gives me a 3n minus 1. Here 3n minus 3n is 0, so I'm just left with the 8. And now I undo subtraction first. So I undo subtraction by adding the 1 to each side. I almost read an 8 like a crazy person. And now I undo multiplication using division. Oh, clearly I should be writing that in blue, right? Yeah, get with the program, Mr. Jansen, you crazy guy. So now I've got n is less than or equal to 3. Now I'm just going to draw a quick graph. I'll draw it off to the side over here because I kind of ran out of space. And again, there's an equal to condition, so use a closed dot. Less than, everything to the left. Okay. Again, the n is less than or equal to 3 is my answer. The graph is just there as a visual representation, and later it'll be used to check our answer. Okay. If I look at the next one, again, same kind of thing. I want to simplify and then solve. I simplify by doing my distributive property. So I'm going to distribute. And now once again, I can't combine anything because they're on different sides. So I have to get rid of one of those minus 8a's. So I'm going to add 8a to each side. I'm going to add this 8a to each side to get rid of it so I can get my a's together. But once again, what happens is kind of the strange situation of all the a's go away. I end up with 10 is greater than or equal to 10. So once again, I have to just decide, is that a true statement or a false statement? Is 10 greater than 10? No. Is 10 equal to 10? Yes. So is 10 greater than or equal to 10? And the answer is yes. Okay? That or is really important because it's one or the other. Is 10 greater than or equal to? Well, yes, it's equal to. So the answer to that or question is yes. This is a true statement. So it's all real numbers. And if you remember, the symbol for all real numbers is that R with a bar on it. Or you can literally write out all real numbers and that will be fine. Okay? False statement is no solution. True statement is all real numbers. Okay? If I look at the next one, simplify and then solve, just like we do with equations. I'm going to simplify with my distributive property. 3t plus 3. And now if you look, those t's are on the same side of the equation, so I can go ahead and combine them. 3t and the minus 4t is a negative 1t. And now I can undo order of operations and undo the operations as I go. So I undo the addition by subtracting 3 from each side. And clearly this is a job for my red marker. I don't know why I tried writing in green. That would be insane, right? And now to undo multiplying by a negative 1, I'm going to divide each side by a negative 1. Whoops, I changed my inequality symbol. And that's a common mistake that many students make. Don't fall into that trap and change it to an equal sign, okay? Don't follow crazy Mr. Jansen off a cliff here. So let's see, here I get a t, and now because I divided by a negative, I have to flip the inequality sign. That's the only difference between this and equations. And now negative 8 divided by negative 1 is a positive 8, okay? Again, that's my answer, but I'm going to draw a quick sketch of it over here. No equal to condition, so an open dot. Less than, so I shade to the left because that's where the smaller values are, okay? And again, we could use that to check by like plugging values like the 7 back into the original inequality. It should give us a true statement because that's what's shaded. And if you forget to flip that inequality sign, if you plug a 7 in, or a 9 in, rather, it's not going to work, okay? So please remember, when you multiply or divide by negative, you've got to flip that inequality sign. And then if we look at this one, you have 42 feet of fencing for a vegetable garden. If the garden must be 12 feet long, what are the possible dimensions for the width? And again, whenever you have a word problem like this, draw a picture, all right? There we go. It's a rectangular garden, 42 feet of fencing. Let's see, it's got to be 12 feet long, so this has to be 12 feet. And I know how rectangles work, So this has to be 12 feet too. What I don't know is the width. So I'm going to call it W because I have no idea what it's supposed to be. So right here, I'm going to call this W, which means this also has to be W. So now when we think about this, the amount of fencing, we're talking about the perimeter here, right? We need a fence around the whole thing. If I only have 42 feet of fencing, it means when I add up all four of those sides, it's got to be less than or up to 42 feet. It can't be more than 42 feet. And so hopefully you're starting to think about an inequality here. If I add up all these sides, let's see, 12 plus W plus 12 plus W, just working my way around, that's the perimeter. Well, that could be equal to 42 at the most, right? Do I have to use all of my fencing? And that's really the question here. Could I make it smaller? Could I have fencing left over? And the answer is yes, which means this guy has to be less than or equal to 42, okay? And here's the thing. You could solve that with an equation, just say equal to 42, but then you're not thinking about the possibility of having a smaller garden. Maybe you don't want to take care of that much in terms of the size of that garden. Maybe that's too big, all right? And so that's why we have the less than condition. It's okay to have fencing left over. What we can't do is go bigger than that 42 because we don't have enough fencing. And so now I simplify by combining like terms. So I've got the 2W and the 24. I undo addition by subtracting. And it looks like that gives me an 18. Oh, and there I went again. I dropped my inequality symbol. Let me fix it. And now to undo multiplying by 2, I'm going to divide each side by 2. Let me write my answer up here. So I get W. It's still a less than or equal to symbol. And it looks like a 9. Okay? So again, interpreting this in terms of the word problem, my width, okay, so the width has to be, be 9 feet or less. And here's the thing, you could write this as an equation and solve and get the 9 feet, but when you interpret the answer, you still have to make sure you include that it has to be 9 feet or less to make sure that you don't run out of fencing, okay? So again, solving inequalities is the same as solving equations, except if we multiply or divide by a negative, you have to flip the inequality sign. When we graph them, equal to condition is a closed dot, no equal to is an open dot, and then shade the appropriate side, okay?